Okay, so let's talk about ensemble learning and random forests. We'll talk about the different forms of them. So the point of ensemble learning is you have a machine learning model which is useful, but not, it has some degree of making errors, like a series of if statements, a decision tree, and you want to improve that. So what you do is make an ensemble of multiple learning models and combine the outputs to be better than they are alone. And you can do it with a random forest, which is just the forest implies it's a group of trees and it's a bunch of decision trees. And you train them on different subsets of the data so they will be different and then combine them. And this is, as I mentioned last time, this is one of the most powerful ways to make a strong machine learning. So you could have diverse classifiers where you have different things here like support vector machines, random forests, and these logistic regressions and other things where they have completely different machine learning models implemented, and therefore combining them, you're more likely to improve things because there'll be different measures of the property you're trying to detect. And then you can decide how to combine them with voting. So if you want to, you can have a majority vote where each one of them, like this one says it categorizes it as one, this one categorizes it as two. So you could take the majority vote and decide the ensemble has decided this is category one. That's one way to do it. And of course, anytime you're trying to average multiple measures and hoping the noise will cancel out, what you want is for the measures to be independent. So they have different noise. And one case where this fails, for example, is RAID arrays. RAID arrays have a series of hard disks, like 5 or 7 in a box, and they all work together. And the idea is if one or two drives fail, you don't lose the data. But I've talked to data recovery companies, and they say what frequently happens is many of them will all fail at once because they're not really independent. It apparently in practice is not true that each of them just has a random chance per day of failure. What happens probably is it has something to do with the way they're used or the power fluctuations, and frequently a bunch of them will all fail at once. And that is when, even though you have multiple contributing items, they're not independent, so it doesn't cancel out the noise. So, and this is the law of large numbers. You know, if you do a coin toss, you expect to have 50%. But if a small number of coin tosses, you might have a significant deviation. But as you increase the number of tosses, the error will go down. And in a simple case like this, it goes down as the square root of n. So, all right. So then you can find some way to take your group of your input data, which is a bunch of instances, and use it to create algorithmic diversity. So you could use different training algorithms or train on different data. So bagging is sampling with replacement, and pasting is sampling without replacement. And so the issue is you have a population, and sampling with replacement, you'd pull, say, a random 6, and then you'd pull another random 6, and some of them might be the same. Like the first one is included in each group because you replace them after each sample and draw them again. All right. Okay. And Diane said that happened to her when she was network admin, probably the RAID arrays. Yeah. They were all installed at the same time. Right. That's the issue. All right. So that's with replacement. And without replacement, you would draw a sample, and then you draw a sample of the ones that haven't been used yet. And again, the ones that haven't been used yet. So both of these will probably be the same for large data sets. But anyway, so now you have these predictors that have been trained in some way differently with either different subsets of data or different algorithms. And then you have hope that they're making independent errors. And so averaging them together will produce a better answer. And so here's an example we've seen before of 500 decision trees that can create an average of all this. And here's decision tree with bagging, which we're going to explain, I think. And we go back to bagging here. Yeah, with replacement is called bagging. And I don't, yeah, here's, I think one, yeah, sorry, I'm afraid I don't quite understand the point of this one. This one is certainly better. This might be just a single tree. There we are. This is a single tree, which we have seen before, which if you let it go to a high depth, it will create this complicated shape, which is not accurate, and somebody's asking about attendance. No, I haven't done that yet. I'll do it after the lecture. Anyway, but if they're bagging with a lot of decision trees, you average them together, and it has the effect of smoothing things out to be a better representation of the underlying data. That's the idea. So you draw a certain number of these with replacement. It will only use 63% of the samples, drawing some samples twice or more, and that's the game here. So, all right. Then you've got random patches and random subspaces. This is the one we talked about. What we've been talking about so far is where you choose random instances, but each instant you would keep all the features. But here you could choose not only to sample only some of the training instances, but to take only some of the features of some training instance. Remember, each instance has a bunch of different measures of a bunch of different input parameters, and you might choose to only include some of the parameters. Another way to do it. All right. And then you can have a random forest, which is just a group of decision trees trained by bagging, and that will create tree diversity. All right, you have extra trees where you'd have a random threshold value. This is amazing it works at all. Instead of optimizing the decision tree to choose the best threshold to most efficiently separate the data into categories, you just choose random features and random thresholds. That's called extremely randomized trees. And sometimes that's better. That would seem kind of crazy. Each individual tree is not doing a very good job of separating things at all. But the end result is if you combine a lot of them, it might actually work. And so here's another one that's interesting. If you look at how much a node using a particular feature reduces the impurity to see how effective it is, you can decide what part of which features are most important. And this is for the MNIST data set, where you have these handwritten numbers, and you're trying to identify them. And here you can see how important various pixels are. So pixels in the center are extremely important. Pixels around the edge are not important at all. And this is useful in understanding what part of the input data will be used. And we're going to see more tests of this later as we see what parts of the input data are most important. There's other ways to measure that too. When we get to principal component analysis, you'll see how you can again take this 784 pixels and figure out which part of it is really the most important. All right, then there's boosting, which is hypothesis boosting, and this is any way of combining a bunch of weak learners into a strong learner. So you can train them sequentially. This is one possibility, each trying to correct its predecessor. That's the plan here. And so there's eta boost and gradient boosting. So what you do is you have one model, like a decision tree, that you train, and it has some efficiency, and it captures some portion of the variation. So now you have another predictor that will pay more attention to the ones the previous one failed and try to correct the errors of the previous one. So you have a successive approximation series here. And so with learning rate equals 1, your first match will be here. And then after you add the second correction, the boundary will move here, and the third, fourth, and fifth correction will end up here. So your models are going to jerk from one set of instances to another. But with slower learning, it will converge. And this is adding first approximation and then another level of correction and another level of correction to try to get a well-defined boundary between these two data sets, these two sets of points. And here's another gradient boosting, where you fit each predictor to the residual error. So first you have a simple one, then you take the residuals. So this part is above, it is above the prediction, and this part is below the prediction. So you subtract out the first approximation and fit the residuals to another decision tree, and then residuals to another decision tree. So that's gradient boosting. All right. And so if you have a low learning rate, then it will generalize better, but it takes more trees. And early stopping is the technique I mentioned before. The place to stop is when adding more trees does not improve the result. And this is generally true for all machine learning models that involve taking steps like stochastic gradient descent. You're getting better, 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 better. And when you start getting worse, then you stop. you have apparently hit the best. All right. So you can bin the input features. If you want to do histogram-based boosting, you bin the input features into bins, replacing them by integers, and this will make it more efficient to run faster. And this is reminiscent of another thing, true of large language models. Large language models take enormous amounts of GPU to calculate right now, and people are trying to find ways to make them faster so you can run them on cell phones. And one thing that works is to quantize them. Instead of having 16-bit integers or floating point numbers in your matrices, you boil it down to just 8 or 4 or 2 bits for the weights and the calculations intermediate, greatly quantizing them down. And in practice, they still work very well and are much faster and consume less memory. So that's another thing you can do here. You can basically go analog to digital conversion and approximate things with a small number of bins, like 255, to make it run faster. And the precision loss will act as a regularizer. And of course, the calculation will get much faster. All right, another thing you can do is stack them. We talked about hard voting, how you would have just take the majority. You had 3 classifiers. Let me go back to this one, because here's a subtlety. Yeah, the NPU on the smartphone would help. But if you go back here we had 3 of them said 1, and 1 of them said 2. So we decided the answer was 1. But really, we haven't preserved all the information there. Each one of these is putting out an analog signal, like a value, where if it's above 0, it's a 1. So this might be like a signal of 100, and this is a signal of 200, and this is a signal of, say, minus 50. And you could take the actual analog values here and combine those to use more of the information coming from each classifier, rather than each classifier just boiling down to a categorization like 1 or 2. This is hard voting, where each categorizer has to completely settle on the categorization, but we could use a smarter way to mix the data together. And so the final predictor is a blender or a meta-learner, the one that combines evidence from the ones below it. And so here they'll have analog outputs like 3.1, 2.7, and 2.9, and you can blend them to make a more stronger predictor. And so you can train the blender to just use machine learning to find the most efficient way to combine these, because some of them might be more reliable than others. Some of them might be accurate and others less accurate. And so you let machine learning decide the smartest way to combine the outputs. And then you can have 2 layers of blenders even. So you have the input, the original classifiers here that are trying to decide which digit you see, and then you have these that are trying to blend them, and then another one trying to blend those. There's just another way to do it. All right. So that's what I wanted to tell you about these decision forests, ensemble learning and random forests. So let me stop this recording.